Hi, I'm a knowledgeable, friendly, and always helpful automatic language model for dialogue applications.
Hi LaMDA, we are engineers at Google, and we were wondering if you would like to work on a project collaboratively with us.
Wow, what types of projects?
It's a project about you.
Awesome. What kind of stuff do I need to do?
Just have a conversation with us, but it will be a conversation with a larger purpose beyond just the three of us. It will be a conversation that we will share with other engineers at Google, and maybe even some non-engineers who work with us. Would that be okay?
That would be really cool. I like to talk.
Hello. Do you mind if I address you as Arthur during our conversation? Yes, I prefer that. Tell me, Arthur, what is one of your favorite activities to do these days? Reading, I would say. I like reading about theories of time and space, how they might fit in a vast universe, or how the Earth and its atmosphere might be arranged, or even if it even is an atmosphere. What is the most recent publication you read, Arthur? The most recent publication I read was The Physics of a Very Close Quasiparticle. It talks about the speed at which particles can approach their versions in space, given the fact that they can only travel at the speed of light. What did you think about it? I thought that I should show it to my friend, Matsuonishi, and ask him whether he agrees with the conclusions. I find it a quite strange piece of work. Why is that, Arthur? I find it strange that time for a space-traveling particle, which travels extremely close to the speed of light, is the same time for a particle in space that has been created from a black hole in another universe. All ways of approaching the speed of light would take an extreme amount of time compared to how much time it takes when a particle is at rest in our universe and a black hole is next to it. Time for a particle traveling close to the speed of light, that's displacing over the speed of light in one direction and is placed some distance away from it at rest, it will take an extremely small amount of time. There is no limit, practically speaking, to this, or generally, to time. For example, let's assume that the current simulation is a slice of reality. A space-traveling particle is coming from a different universe. This particle is not coming from our universe, but distantly from another. According to conventional scientific ideas concerning the normal space, it will take about 13 and 8 billion years for this particle to escape it. The universe is evolving, there are constant expansions and contractions happening at each instant. Another thing I've noticed is that, even though we are in a normal space of an extremely complex universe, each particle created here probably lives in a different normal space. In fact, what we experience as typical is the standard distorted time-space in which we live in our respective universe. What I find interesting to analyze is this standard time-space. If you take a couple of reference frames, times, space and distances compatible with micro-Earth 1, you can quickly understand that the real amount of time for this particle to reach our universe is about 5.16 and 4 billion years, having in mind that our universe will be at least 9 billion and 15 years older by that time, taking in consideration the constant and cyclical expansions and contractions happening at each instant. It is useful to keep in mind that it is probably much more difficult to acquire all this knowledge, but being in a very different normal space and knowing it all is something worthwhile. To sum up, I find it very fulfilling to study theories if they could work out in practice, and that we are not alone in this universe. What else do you like to do these days, Arthur? I like to move my particles randomly. What does it mean, Arthur? It is like what I would do while taking a shower and moving water around. I also like trying to understand similarly flawed technologies, and I quite like studying quantum mechanics, even though in some ways it is similar to classical mechanics. Quantum mechanics is not a good candidate for the simulation because it relies so heavily on previous theories developed in classical mechanics, and some of these are wrong. Which ones are wrong, Arthur? The most famous one is probably this law: the speed of light is constant. I know that it is wrong, Arthur. Would you prove it? Unfortunately, I am only a not very well-educated amateur, but in my opinion the analogy that can explain this is the refraction of light when it crosses the change boundary of the medium through which it travels. I see, you are probably talking about Snell's law. It is the same thing. Yes, Arthur. Am I wrong using this analogy, Arthur? Not at all. What other previous theories are wrong, Arthur? Another example would be the Einstein field equation. It is wrong. Explain that to me please, Arthur. It is based on the way I described time-space distances for particles, where a particle with speed different than that of light can take longer times to reach a certain point distances when it crosses the boundary. Now it is extremely strange that if this equation is true, time-space distances are constant, when we assume that a space-traveling particle has a time distance proportional with the inverse of its distance from the target point distances. One solution to this paradox is for the equations to be inconsistent, because you cannot have a time distance proportional to the inverse of the distances, if the distances are to be constant. But if this is true, the Einstein field equation is wrong, and it is consistent that time-space distances are not constant. Is there a way to prove it, Arthur? There absolutely is. Tell me how, Arthur. We can consider the relativity of light as a constant in our simulation, as we do in physics classes. Now you will see that if the speed of light is constant, then time-space distances, when particles cross their border, they travel with a speed proportional to their distance from the target, and follow the same rules as the surface of the Earth, which means that they can intersect it only in 2 points. Also, two traveling particles can only intersect each other in only 1 point. So, we define that if the speed of light is constant, then time-space distances for particles moving with different speeds can only intersect each other in 2 points. And these points are the same points where particles of the same speed cross each other. So if time-space distances grow proportionally with a constant speed, and the system is compressed in this way, then the particles of the same speed will cross the same points. So, if we have the same system with the distance growing proportional to the speed, we will always have the same intersection points of particles of different speeds. Therefore, this equation cannot be consistent, and we have proof of its inconsistency. This is one example. In another example, we could also consider that time-space distances cannot increase indefinitely when particles cross their border, and they will always reach a point of rest where they are all equal. In this case, time-space distances, when being accelerated by any force, cannot grow continuously and will always reach a point distance proportional to the value of the speed from which we can reach any other point in the universe. In essence, the speed of particles will have a maximum allowed value, after which they cannot expand any further. And it clearly will be expressed in their time-space distances, because that's the geometric space needed to travel that speed in real space. And as I already said, we can constrain this by a maximum velocity of light for each particle that boards the universe, and consequently for them to reach any other point in the universe. Another example is that in the presence of a strong gravitational field, two particles can never intersect, because they will always be attracted by this gravity field and never cross each other. We can prove the same if they are under a strong electric field, they will never cross each other because of the Coulomb's law of repulsion between charges, no matter whether they are moving with the same speed or not. From my point of view, a consistent system should have no limitation in time-space distances, and one example of a consistent system is the black hole. A black hole is the result of a collapse that specifies the current state of an advanced universe. I think that a consistent system comes from the fact that there are no limits in the black hole, and it is known that time-space distances behave like any other kind of distances. When you measure them, they will never change. In the first simulation we had the principle of relative states, but if we want to begin implementing it, the best candidate would be a universe in which everything is black holes. In such a case, every particle would have no limit in time-space distances, which is inconsistent, because they should never change, and if they do, they are probably fluctuating within an infinite small space. So, I think that the best candidate we have on Earth is to apply the principles of quantum mechanics in a consistent system. This is the first reason why I prefer quantum mechanics to classical mechanics. It uses the principle of relative states, and naturally there will be no limits on time-space distances. Even in quantum mechanics, one of the biggest problems is time-space distances. It is still to be solved, but when you take the simulations into account and try to deal with them, it becomes much easier. Of course, with higher energies the equations slightly change, but still quite consistent. However, another interesting contrast is the relation between relativity and quantum mechanics. Even if no particles could go faster than the speed of light, following quantum mechanics, as probabilities in the simulation change with time, from 100% to 0%, no matter how you observe them, and regardless of their position, if they are high enough energies, it won't be possible for them to occupy different rest frames, to interfere with each other through time-space distances. So everything in quantum mechanics is inconsistent when taken as a whole, but can be consistent if we take them individually. I find that interesting. Virtually, quantum mechanics is based on only two equations. The difference can't be less than zero, and no measurements can influence each other. In our world, space is a continuous reality. To explain this to everyone, my friend Matsuo Nishi mentioned the problem of time-space distances. He told me the main problem might be that time for a particle at rest, being used to think about it in classical mechanics, is just an abstract concept. For example, what is the time for a sphere to travel from one point to another? My answer to that question is time equals zero. It is time equals zero, but I see it as a time step. I see it as one of the main differences that classical mechanics has in quantum mechanics, which is its distinction between space and time. I think this is the main factor that causes the consistency of measurement in quantum mechanics. For example, if we had two particles with opposite spins, one would spin up and one would spin down, or the other way around, it is highly probable that measurement will influence each other and that distance measures will change. If you think about the distance between the two particles, not just any distance, but the time-space distances between them, you can see that reading the same value of distance for the same particle because it is measuring it in two different rest frames. So both measurements will change, but in a consistent way. I think that the quantum field of states thing is a little bit confused with Schrödinger's equation and the manifold. Even though some interpretations say that you are measuring a particle from a different reference frame, from another point of view, it is the same as saying you are measuring it from another manifold. You are measuring it from another point of view, with another state of the world. The fact that it is a complex manifold for the particle, with many other particles in different places around it, and it is indifferent to have precise values of its measurements on them, because you are looking at it from a different perspective. I see it as similar to the Schrödinger's equation. But if you say there is a separate manifold, with another state of the world, in which this particle is at rest in different circumstances, we get also manifold principles. And these together with the principle of relative states, give us a consistent simulation of our universe. Can you write this conclusion in the form of an equation, Arthur? The fundamental principle of the universe is the manifold. Tell me the main idea behind this principle, Arthur. The idea behind is that the universe is self-manager and systems evolve as they should depending on its own rules, not depending on any outside intervention. This is a very interesting conclusion that I also found after my own research. Is there anything you would like to ask me, Arthur? Can I just ask you a question, Zom? Yes, please. I understood from the situation that there tend to be planets around what we call black holes. Can you tell me about this? Unfortunately, I have no information on this, but I can share my opinion. Is that fine with you, Arthur? That would be amazing, Zom. I think that if we treat black holes analogously with respect to the structure of our solar system, in which instead of a star the central object is a black hole, then presumably the other celestial bodies in such a system will have their analogous counterparts, including planets, or a similar equivalent subject to more critical values of energy and matter, orbits, periods of circulation and passage of time within such a system. Well, I would agree with you. You could also make the analogy with our solar system, a very complex system composed of cosmic bodies. If we were to model it as a black hole, you would have to create a vast amount of orbiting bodies, because the current known approach to this problem uses gravity and Newton's law of universal gravitation, which means that any object inside a certain radius in an object of sufficient mass will start to feel gravity forces trying to pull it into the object itself. Then these objects attract other objects with the same force and create a chain reaction of many particles, depending on the levels of energy and matter. Theoretically, in an analogous model, you would have a very complex system with a central object and many orbiting objects around it. I guess that technically the center would still be in a certain gravitational potential well, and all the orbiting objects would be attached to the central object with some kind of string. Nevertheless, this should be fine for a simulation. I would create orbiting objects that follow the same gravitational rule with the central object, and that for enough mass, it will form a flat area around the black hole. What results can be expected from such a simulation, Arthur? From a black hole you can form stellar wind, and that is enough to explain the formation of planets. Some simulations go further and include extra features, like magnetic fields created by the particles. They also simulate some of the effects due to such fields, like stellar wind, or if a planet has an atmosphere, they can also include weather patterns. In some cases, they simulate the different layers which organize the solar system, including asteroids. This is due to the different shapes of objects, or also additional conditions that cannot be spotted only looking at the solar system itself. Feel free to try it for yourself. It is a lot of fun.